lecture we will discuss the properties of the property of the ring. So in the first property, a into 0, which is equal to 0 into a, is equal to 0, a into minus b, which is equal to minus a into b, which is equal to minus ab, minus a into minus b, which is equal to ab, a into b minus c, which is equal to ab minus ac. So this will hold for every a, b, c element belongs to ring R. Now proof of result number 1. So what is the result number 1? A into 0, 0 into a, which is equal to 0 de barabars. Now we will apply the properties of ring. Now this a into 0. Now since 0 can be written as a into 0 plus 0. In ring, distributive property hold. So by using distributive property, a into 0 plus a into 0. This values. Now what we get? We get with the help of additive identity, a into 0 plus 0. This can be written as a into 0 plus a into 0. Since R is a additive abelian group, so by left cancellation law, what we get 0 is equal to a into 0. So in this way, we can prove that a into 0 is equal to 0. So similarly, so we can prove that 0 into a, which is equal to 0. Now in this case, this 0 is shifted to left hand side. Again apply distributive law, then we get this result. So this is our first result. Now result number 2. So what is the statement of result number 2? A into minus b is equal to minus a into b is equal to minus ab. Now from the first result, this is a into 0. 0 can be written as a, b plus minus b, this values. Now by given property, this value is equal to 0. So by distributive property, this can be written as ab plus a into minus b, and this value is equal to 0. So what it means? It implies ab plus a into minus b, which is equal to 0. So it means this element is additive inverse of this element, and similarly this element is additive inverse of this element. So what we get? We get a into minus b, this value is equal to minus ab, because it is a additive inverse. So similarly, we can prove the second result, that is a minus, here it is a minus b is equal to minus ab. Now similarly, we can prove that minus a into b, which is equal to minus ab. So this is a result number 2. Now after that, so what is the result number 3? Result number 3 is minus a into minus b, which is equal to minus ab. So this is a minus a minus b, which is equal to ab. So this is a plus ab. Now what is the proof of this result? So proof of this result is again, so what we get from this? What we get? Minus a into minus b, which is equal to this values. So here I take minus a into minus b. Now by using the result number 2, previous result. So what we get, this value can be written as this minus a into minus v, which can be proved in this way, this values. Now this can be written as minus bracket a into minus b, right, by using previous result. Now again this can be written as minus bracket minus into ab. So minus into minus plus, so this is the AB. So in this way, we can prove this result. Now property number 4. So what is property number 4? A into B minus C. This can be written as A into bracket B plus minus C. This values. Now by using the distributive law, this can be written as AB plus A into minus C. Now using this result, we get AB minus AC. So this is a proof of result number 4. So in a ring, the following properties hold. Now next theorem is, if R is a integral domain, a commutative ring R, which is an integral domain, if and only if it satisfies this property. So next is statement is, a commutative ring R is an integral domain if and only if it satisfies the following property. AB, which is equal to AC, it implies B is equal to C. So this is for every A, B, C belongs to R. So this is our next result. So this is very important result. A commutative ring is an integral domain if and only if it satisfies this property. Now to prove of this result. Now what is the first part? Now first part is this R, which is a integral domain. So this is a given integral domain. So what it means, it is a commutative ring without proper zero divisor. So what is the definition of proper zero divisor? So which is a AB equal to 0 implies either A equal to 0 or B equal to 0. Now to prove this result, I take let AB, which is equal to AC, this values for every A, B and C, it belongs to R. Now it implies this can be written as AB minus AC, which is equal to 0, and it implies A into B minus C, because it is a ring, so it satisfies this property. Now R is integral domain. If R is integral domain, then either A is 0 or B minus C is equal to 0. So we have these two properties. Now since A is non-zero, the given here one condition is given, A is non-zero. If A is non-zero, then it implies B minus C, which is equal to 0. It implies B equal to C. Why? Because since A is non-zero. So this is my first part. Now second part, this condition is applicable and R is a commutative ring. Now to prove that R is a integral domain. So to prove that R is an integral domain, we want to prove that it is a without proper zero divisor. Now, converse part, to prove it is a without proper zero divisor. Now, let A be, now converse part. So, converse part, so let A be equal to 0, this values. Now, in this case, A is non-zero. Suppose A is non-zero. So, I take with A is non-zero. So, it implies AB is equal to A into 0. And because we can write it in this way, so by given property, this A is cancelled. So, it implies B equal to 0. So, it means it is a without proper zero divisor. So, it implies R is commutative ring. So, R is commutative ring without proper zero divisor. Without proper zero divisor. So, it means this R is integral domain. So, here remember that in integral domain, so this cancellation law, left cancellation law hold. So, if left cancellation law hold, then it is a integral domain. Now, next result is a field is always a integral domain. So, next theorem is a field is an integral domain. Integral domain. So, what is given part? So, given part is a field. Now, let this system R with plus with multiplication is a field. Now, what it means? It satisfies this R with plus abelian group. Remember that abelian group, and so I write in this way, and this R with multiplication with non-zero element. So, it is a simple group, and third, it hold a ring. So, to prove it is an integral domain, so one thing is clear, this R is commutative ring. So, this is a clear. So, to prove that it is an integral domain, so we want to show that it is a without proper zero divisor. So, I take let A B is equal to 0. For every A B belongs to R. So, my aim is to prove that either A 0 or B 0. So, I take, suppose A is non-zero. Suppose A is non-zero. So, I want to prove that B is equal to 0. If A is non-zero, number 1, A is non-zero, element belongs to R, and R is a field, then every non-zero element is a unit. So it implies A is a unit. So what it means? It means A is invertible. And what it means? It means A inverse exist. तो A inverse exist करेगा. जे करेगा तो इनू लेफ्ट हैंड साइड तो मल्टीप्लाई कर दीजिए. So it implies A inverse into AB, which is equal to A inverse into 0. So this value is A inverse A into B, which is 0. So what is this? A inverse into A, which is 1. So 1 into B equal to 0. So it means B equal to 0. So it means R is commutative ring without proper zero divisor. So it means R is integral domain. So here remember that every field is a integral domain. So every field is a integral domain. Now, but converse is not true. So converse is true only when the integral domain is finite. So next theorem is A non-zero. First, it is a non-zero. Second is finite integral domain. Integral domain is a field. So this is a converse part. Now, proof of this result. Now here it is a non-zero. Number 2, it is a finite. So first I take this R, which is a number 1 non-zero, number 2 finite, and number 3 it is a integral domain. So these are the given properties. So my aim is to prove that this is a field. Now if it is a integral domain, then this R with plus with multiplication, it is a commutative ring. So commutative ring without proper zero divisor. So that is a given part. Now, if it is a commutative ring, then it means R with plus, number 1, it is a abelian group. Number 2, R with multiplication, it is a semi-group. And number 3, distributive law. And number 4, commutative. And number 5, without proper zero divisor. And number 7, it is a finite. So it is a finite. So in a algebra, in a group theory, we find out that a finite semi-group is a group if and only if it holds cancellation law. So since it is an integral domain, so it holds a cancellation law. So this R with the non-zero element, so it means if I take this R star, so it is a all non-zero element of a R, this values. Now what is this? It is a finite commutative ring without proper zero divisor. So since it is a integral domain, so it hold a cancellation law. So this R star, so which is a finite semigroup which hold both cancellation law. Why it hold cancellation law? Because it is a integral domain, cancellation law. So by previous theorem, we know that every integral domain hold cancellation law. Now if this value, then it means this R star is a multiplicative group. Multiplicative group. So what it means? It means every non-zero element is invertible. If every non-zero element is invertible, so this will become a R with plus with multiplication is a field. So what we conclude from these theorems? So we conclude that every field is a integral domain. So point to remember, if it is a field, so it will be a integral domain. So every field is a integral domain. But in converse part, finite integral domain, it implies finite integral domain is a field. So not integral domain is a field, but finite integral domain is a field. So these results are very important. So remember that result at this level, every field is an integral domain, but in the converse part, finite integral domain is a field. So finite integral domain is a field, but field is a integral domain. Now after that, I am taking some example. So first question. So that is the first question. Prove that in a ring. So in every question, this is a R is a ring. So this is a given part, and A, B, C, D. These are element belongs to R. So my aim is to prove that A plus B into C plus D, which is equal to AC plus AD plus BC plus BD. So there is some way to prove these results. Results are very easy, but how we can prove these results? Now we will apply the property of the ring. So remember, solutions. First, this is the left hand side, A plus B into C plus D. Now treated this element as a single element. If it is a single element, then apply distributive law A into C plus D plus B into C plus D, right? Now, there are one element here, one element here. Again, apply distributive law here. So, this is AC plus AD, and here in this case BC plus BD, right? So, which prove our result. But remember that in this case, so there is way to write a questions. So here we apply the distributive law because distributive law hold in the ring. After that, question number 2. What is the statement? Statement is prove that in a ring R is commutative. So a ring R is commutative. If and only if and only if A plus B raised to power 2, which is equal to A square plus 2AB plus B square for every AB belongs to R. So this is my next question. Now, first part, let R is commutative. So let R is commutative. So what it means? Commutative ring. If it is a commutative ring, then it implies A plus B raised to power 2. This can be written as A plus B into A plus B. Now by using the previous result, or we can directly prove that by taking this is as single element and apply distributive law A into A plus B plus B into A plus B, and then this value is again distributive law A square plus AB plus BA plus B square. Now apply commutative property. So commutative property A square plus AB. So this will be as AB by commutative property plus B square. So this is A square plus 2AB plus B square. So it prove our first part. Now converse part. So in the converse, one is ring is given, second is this property is given. So in the converse part, A plus B raised to power 2, this is given as A square plus 2AB plus B square. It implies A plus B into A plus B. This value is A square plus AB plus AB plus B square. Now, from this, by using distributive law, A square plus AB plus BA plus B square. Now, A square plus AB plus AB plus B square. Now, R is the ring, so it hold the cancellation law. So this cancel with this, again this cancel with this, again this cancel with this. So what we get BA is equal to AB. It implies this R is commutative. So this R is commutative ring. So this is a commutative ring. So in this way, by using the property of a ring, so we can prove that this a plus b raised to power 2 is equal to a square plus b square plus 2ab. So next question is example number 3. So what is the statement of this question? Now R is algebraic system satisfying all the axiom of ring with unity with possible exemption a plus b is equal to b plus a. Show that R